morning. Now that we have developed a rationale to determine under what conditions a rapid release of energy gets generated in an explosion in the particular context of a lump mass system, let us go ahead and see whether we can relax this assumption of this lump mass system and see whether we can understand the explosion a little better. Therefore, in this context, let us restate what we have been saying all along. In the lump mass system, we said, well, the temperature is uniform throughout, concentration is uniform throughout. We assume all events to occur in the spatial domain at uniformly at all times. Well, this just may not be possible. Like for instance, we again go back to this example of a hydrogen oxygen mixture. In this particular one, let it be at a pressure of 1 atmosphere, initial temperature being around 300 Kelvin, and I sort of deposit some electrical spark or some energy in this particular small volume. It is not that the entire volume is going to explode like what we assumed in the lump mass system, but all of us know, yes, from this particular source of energy which is released, this energy release heats up the neighboring volume, and so on. A zone of chemical reactions propagates out. Let us take a small look at this. Let us therefore expand this particular portion and maybe sketch it over here. In other words, I have a small volume, now I show it little magnified, in which I deposit some energy over here in this small volume or in a small volume corresponding to the electrical spark or some resistance heating, whatever it is, or a matchstick I put over here and I heat the gases over here. What happens? The moment this volume gets hot, maybe chemical reactions take place and maybe the temperature goes up still further, and what happens? This gas heats up the neighboring gas around it. That means, in a zone which now I show in pink over here, the neighboring gas gets heated by the chemical reactions and heat generated in this small volume, and the heat sort of diffuses out, the concentration diffuses out, causing maybe a chemical reaction in the adjacent layer. And now what further happens? This adjacent layer, which is therefore hot and it undergoes chemical reactions, heats up the next layer over here. In other words, I have the adjacent layer to the one which was previously heated, now getting heated by heat transfer or conduction or convection from this pink zone into it, and chemical reactions occur in this particular zone, and this zone thereafter further heats up the layer around it and so on. And therefore, what is happening? This zone now heats up the zone adjacent to it, and in this way, from this initial zone of heat release, you have chemical reactions occurring here because of heating. It causes chemical reactions in the next layer, it causes chemical reactions in the next layer and so on. You have chemical reactions propagating out from this zone of heat release, rather you have propagating out till it fills the mixture. Therefore, it is not that instantaneously, as assumed in the lump mass system, everything is uniform, but it is going to take some time for it to propagate out. This point 1. Point 2, let us take a look at the energy release itself. Supposing this volume is very small, let us say, maybe this volume is small and the amount of chemical reactions it produces are small, such that when it heats the next layer, apparently it is going to get cool because the heat passes on to the next. Therefore, this hot zone becomes cool, and if the volume is sort of insufficient, or if the amount of energy here is insufficient, or the amount of chemical reactions here is insufficient to be able to maintain its temperature as it is heating the next layer, what is going to happen? This initial volume, which I showed something like this over here, this initial volume, the amount of heat in it will collapse, or the amount of temperature in it will decrease, chemical reactions will decrease, and by the time the neighboring element gets heated up, well, it is inadequate to heat the neighboring element and it collapses. Therefore, the spark or the chemical reaction collapses and I can no longer be able to get combustion occurring in the neighboring layer. Therefore, we say, well, I use a spark for igniting a mixture, and unless I have adequate quantity of this particular volume, or let us say by volume I mean something like a kernel, something like a seed. If I do not have an adequate kernel for ignition which takes place, well, the ignition kernel will collapse and it will not be possible for it to heat the adjacent layers, and therefore, it is necessary for me from ignition point of view to make sure that the size of the ignition kernel should exceed some threshold value, and this is what I want to do. I want to be able to find out, unlike I am not heating the whole thing, mind you, I am not having the total mass in this system which is equal to rho v in rho density into volume into specific heat into the high temperature, that is the burn gas temperature minus the initial value, that is the, let us say the initial temperature is same as ambient. I do not need to supply that amount of heat, I just need to supply the heat required to really drive or form an ignition kernel which can heat the succeeding layers and allow the combustion wave to propagate out. But to be able to do this, to be able to find the critical size of the ignition kernel and therefore ignite the gases and have a flame moving out, it is necessary for us to get some idea on the rate or the speed with which the combustion wave, what do you mean by combustion wave? Zone of the reacting gases, and whenever you say zone of reacting gases, the temperature increases and therefore the speed at which the zone of the reacting gases move out, the thickness of these zones, and some more definitions before I can go and determine the ignition, and this is what I do today. Having specified the problem, let us see how to go about it. Let us first say, well, what is the speed at which the sort of the combustion zone propagates out? That means the speed at which the chemical reactions are going forward. To be able to do that, let us now say, well, let us forget about curvatures. Let us say I have a zone of combustion. Therefore, I also say, well, I have a pipe or some particular medium in which, well, I have the unburned gases. Unburned gases are at density rho, which is unburned. Well, they are at a temperature Tu, which is the unburned gas mixture, and we can also say, well, the pressure of the unburned gases is Pu. Into this unburned gas mixture, like I have the unburned gases here, into which a combustion wave propagates or the zone of reaction propagates. Well, let this particular zone of combustion, which I now say is planar, is propagating at a speed s meters per second. Let us say s meters per second into unburned gases, therefore, I can as well say it propagates at a speed su meter per second. What happens behind the combustion front which moves into this? Well, the gases burn behind it, chemical reactions take place, and the density, let it correspond to the burned gases, let the temperature correspond to the burned gases, let the pressure correspond to the burned gases. Therefore, the suffix B for pressure, temperature and density, if it is B, it corresponds to burned gases, and the suffix here U for rho, T and U corresponds to unburned gases. Well, this is the problem, and I want to determine, let us say, the speed at which the combustion wave propagates into this medium. And as we did, whenever we talked of these waves which are propagating into a medium, see, we also told, to be able to look at the problem with a wave propagating and things moving. When the wave propagates, well, I should have some velocity within the medium, let us say U in the burned gases behind the wave which is moving at SU. It is somewhat difficult, and the easiest way to do is effect a coordinate transformation such that I imagine I sit on the wave, or I am standing on the wave itself. That means I am looking at this particular problem in the context of the wave stationary. That means I sit on this wave and watch the show. If I were to do that, what is it I get? Well, I have the same problem now. Well, I have the wave front here, but since I am on the wave, in the frame of reference of the wave itself, that is the combustion wave which is moving, or let us say the combustion front which is moving into the unburned medium. Now, since I am here, well, the unburned gases at a density rho u, at a temperature Tu, at a pressure Pu move towards me, that means towards the wave in the frame of reference of the combustion front itself at a speed Su. Let us assume, yes, behind it, well, I have rho B, I have Tb, temperature of the burnt gases, pressure of the burnt gases, and let us also presume that maybe in the frame of reference of the wave, let the velocity be Sb. Well, what is it I am interested in? I am interested in determining the value of Su. Well, the problem is posed, you say, well, behind the combustion disturbance or the combustion which moves, I have these are the values and these are the values upstream. But can I picture what is really in this wave? What is happening over here? What is this combustion front or the zone of combustion which we said is moving? We said, well, something gets heated, I have some diffusion of heat, some diffusion of concentration which causes the adjacent layer to react, and so on. And the same thing is happening here. This causes adjacent layer to react over here, That means gas is moving, more and more of these unburnt things are coming over here, it gets heated. Can I see can I expand this out? Can I have a mental picture of what is going to happen? And that is what we call as a mind model. I want to have a mind model of what is happening in this particular front over here. Therefore, let us try to sort of devise what would happen. Well, we say, well, the unburned gases are moving, therefore, maybe initially I have the unburned gases maybe at a temperature Tu, and then what is going to happen? Well, at the exit I have all burned gases. Now, let us try to expand it out, let us try to give some thickness to it. Let us say initially the temperature is Tu on the left hand side, on the right hand side, well, the temperature is Tb, and what is going to happen? Into this particular one which is representative of this particular line over here, what is happening? I have rho u and at speed Su, that means this is the mass flux which is entering this particular one, and what happens? The moment it enters, initially it is at a temperature Tu, and when it enters, well, you have the hot products of combustion on the right hand side, well, it is going to get heated and the temperature will sort of begin to increase. Well, the temperature begins to increase, and where does it end up? Ultimately, the temperature should be Tb, corresponds to over here. Let us say that the temperature is T of the unburned gases on the left hand side, and what is going to happen? Well, the temperature increases from Tu, and it increases to a level wherein sort of the chemical reactions begin to take place, and once the chemical reactions begin to take place, the chemical reactions occur fairly fast, and therefore, it reaches this and it comes over here. Therefore, this is the way the temperature should change from the initial value on the left hand side, that is the unburned gas temperature Tu, to the burnt gas temperature Tb over here. Well, this is a picture which seems logical, and therefore, I can also tell myself, well, this is going to be my thickness of the flame or the thickness of the combustion front. Very often we call the combustion front which is here or which is moving over here as a flame. That means, flame is a region of chemically reacting gases which generate heat and light, and that is what we observe, and therefore, we say, well, we are talking of the thickness of this particular combustion front to be something like this. Well, if I were to use what little we have learned from the lumped mass system, we told ourselves, well, when the activation energy for most of the substances are high, and whatever happens, initially I have something like a preheat, the temperature increases to some value, let us say Tc. That is the zone in which the cold gases are heated to a particular temperature, which we called as preheat. And once it has been heated to the critical temperature, that is the auto ignition temperature, well, there is a spurt in chemical reactions and the temperature shoots up like this. Therefore, we are now telling, well, initially there is something like a preheat followed by chemical reactions in this particular length, and therefore, now I can put something more. I can say, well, this is my zone of chemical reactions, fast chemical reactions, which I call L. Therefore, I say, well, the thickness of the flame is Tf, my zone of chemical reactions is L, and now can I write an equation for this particular phenomenon? This is the zone of active heat release. Well, this is the zone in which heat gets released. This is the zone in which heat is getting received such that the temperature goes from Tu to Tc. Therefore, what is it we are talking of? We are talking of a zone in which heat is getting released, and this heat gets sort of transferred into this zone such that it is able to increase the temperature from Tu to Tc. Therefore, this zone, that is the preheat zone, receives heat, and you will also observe whenever we receive something, we receive something like this, we put our hand and receive something, whereas when you give something, you give something like this. Therefore, you receive something over here, you give something over here. Therefore, in this zone the heat is being given and the heat is being received over here, and the point of this particular zone or the particular contact between receiving and giving is what we call as the inflection point. Well, inflection point is a point at which the concave downwards in this particular zone, because it is giving, well, it is convex upwards or concave downwards, and what it is receiving is concave upwards or convex downwards, and therefore, the concave downwards is getting replaced by concave upwards, and that is the inflection point. That is, at the inflection point there is a sign in d by dt by dx as a function of dx, wherein I say this is my x distance, and therefore, there is a change in the curvature over here. Well, that is the inflection point. Therefore, rather than carry the concept of critical temperature or auto ignition temperature from the lumped mass system, I say, well, the temperature here is the inflection temperature over here, which is the junction or point at which the heat received from the hot zone is received over here, and this is what is given. I have the inflection point over here. Therefore, now I know the events which are occurring in this particular line over here, which is what I have sketched over here. I want to write an equation for it. And what is the equation? Well, I have to write the heat balance equations. Let's write it out. Therefore, I say, well, I have rho u Su is the mass flux which is coming. To be able to write the equation, let us assume that the area what I am considering over here is unity 1 meter square, and therefore, I say, well, the mass which is entering is rho u into Su into 1, that is the mass flux into 1, which is the mass which is entering. Let us for the present assume it's at constant pressure Cp. We will ratify this assumption a little later. Therefore, this is the thermal mass over here, and what happens in this zone? Well, the temperature increases from Ti to Tu in the preheat zone. This is the heat which is getting received over here. And how does it receive the heat? Well, I should have something like I have a gradient in temperature. It is this gradient which gives the heat, and therefore, this is equal to, again, per unit area. I say, well, the thermal conductivity is K, and I have the gradient which is equal to dt by dx at this particular point, which I can approximate as a straight line over here and write it as equal to Tb minus Tu by the zone length over here. We said this is the length of the combustion zone or the length of the reaction zone. Therefore, Tb minus Ti by L is the gradient, and K into this is the heat flux, and therefore, this becomes my equation 1 for heat transfer. Well, can I now I have put it down. My aim, as we said, is to be able to determine the value of Su, but can I explicitly get an expression for Tb minus Tu, because I find, well, at least the initial temperature I know, I do not know the inflection temperature. Therefore, if I can somehow get, here it should not have been Tu, because what is it I am saying? Tb minus Ti divided by length is the gradient here. Therefore, it should have been Tb minus Ti, and here it is Ti minus Tu is okay, that is the temperature increase. Therefore, if I have to determine this, I know, well, the amount of heat generated in this particular zone. What did we say? Well, the heat generated can be written as the rate of chemical reaction, so much moles per cc into second, into we have to multiply by the volume, so much cc, into we know what is the heat generated per mole, Q, so much joules or kilojoules per mole, and this gives me the value in joules per second, because what happens, mole and mole gets cancelled, Cc gets cancelled, I have joule per second. Well, this is the amount of heat, and therefore, the heat which is generated, since I am considering unit area over here, it is going to be omega, omega I say is the rate of the reactions into V, which is corresponding to the length L over here, which corresponds to the volume, into Q, and this heat, where does this, what does this heat do? You know, this heat, what does it do? It takes this mass flux, maybe the mass flux comes over here, mass flux here, mass flux here, mass flux here is the same. Therefore, the same mass flux comes here. I have rho u into SU into Cp, and what does it do? It increases the temperature from Tb, burnt gases, to from the initial value I to this value. That means I have the mass flux of gases coming over here, which is equal to rho u SU, I am considering unit area, that becomes my mass, into specific heat into change in temperature. Therefore, from this I get the value of the burnt gases minus the inflection point temperature, that is the temperature over here, divided by L is equal to Tb minus is equal to omega into the heat release, that is so much kilojoules per mole, divided by rho u SU into Cp. This becomes my equation 2. Based on this heat release, this is my equation 1. Now, I substitute the value of Tb minus Ti divided by L into this equation, and what is it I get? If I were to substitute it, I get the thermal conductivity K. Let's use the small value of K, because capital K is normally used for something like constants. Therefore, I get K into the value of Tb minus Ti is equal to omega Q into rho u SU into Cp is equal to what is on the left hand side here, which is equal to rho u into SU into Cp into I get Ti minus Tu. Well, now I have to solve, I am interested in finding the value of SU. I solve this, and what is it I get? Well, I get rho u SU Cp square into Ti minus Tu. Let us put that down. I get rho u into SU into Cp square. I move the denominator on this side into Ti minus Tu is equal to what I get, K, that is the thermal conductivity, into the rate of the reactions in mole per Cc second into the energy generated in the reactions in joules per mole, and rather therefore, I get SU square is equal to 1 over rho u square into Cp square 1, and then I also get the value of K omega Q in the numerator on the right hand side divided by Ti minus Tu over here, or rather the value of the speed at which the combustion propagates into the unburned gas medium, so many let us say meters per second, is equal to rho u into Cp into, now I take under root of this side, K omega Q divided by Ti minus Tu. Well, this becomes my expression, and this is the rate at which the flame is propagating into the unburned gas mixture, or the combustion is propagating into the unburned gas mixture. And let us say what are the things which are involved here. We say, well, as the density of the unburned gas mixture decreases, the flame speed increases, point 1. We also say if the unburned gas mixture is at a higher temperature, well, the denominator decreases here. The denominator I am decreasing by a higher quantity, the denominator decreases, and therefore, when the unburned gas temperature is higher, the flame speed is higher. But can I put it in terms of reaction rate? Well, I find yes, if the thermal conductivity is higher, the flame speed is higher. If the heat release is higher, the flame speed is higher. Can I put it in terms of omega? Let us say omega, as you know the rate of a reaction, we defined it as equal to ACN into exponential of minus activation energy divided by universal gas constant into temperature over here, so much moles per Cc second. And we also know, well, we are considering a gaseous mixture for the present, and therefore, I can write PV is equal to n R0 T, or concentration is equal to P divided by R0 T, because PV is equal to n R0 T, concentration is equal to n over V is the P R0 T, or rather I can now write the rate of a reaction. I replace C by P by R0 T, and what is it I get? I get P by R0 T to the power n over here. I also know, well, the density of the gases over here. I can write PV is equal to MRT or whatsoever, and I get the value of rho goes as P at a given temperature, or rather rho u I can write as equal to the initial pressure divided by specific gas constant into temperature, and therefore, mind you, this is universal gas constant R naught joules per mole Kelvin, this is specific gas constant in terms of joules per kilogram Kelvin, and therefore, what is it when I look at this? I get omega to the power half. That means I get P to the power n by 2. I get this is P over here, or rather I get the flame speed. Let me just write it here itself. SU goes as P to the power n by 2 minus 1, because here I get P to the power n, here I have under root sign P to the power n by 2 minus value of 1. And mind you, see, we also told most of the chemical reactions which we consider have n is equal to 2, or rather if you have n is equal to 2, the flame speed goes as P to the power 0, or it is independent of pressure. If it is going to be independent of pressure, well, I know that the speed with which a combustion front moves into the unburnt gas medium is independent of pressure, increases with increase in the temperature of the unburnt gases, increases with the amount of heat release, increases with conductivity, and so on. We have this particular relations, and therefore, let us try to get some feel for the speed. Is it 1 meter per second? Is it 100 meters per second? To be able to do that, let's put the values down, or people have put the values down, and let's see what are the values of the flame speeds that we get. Therefore, I quickly go through a few cases, maybe 2 or 3 gases, and let's try to get a feel for the speed with which the combustion moves into the unburnt gases. Well, I give these values. The values are, let us say I have methane air. Let us consider stoichiometry, that means we say equivalence ratio is 1. At this equivalence ratio, the value of SU is something like 0.5 meters per second. If instead of methane, I just jump to propane air, again at the same stoichiometric mixture, phi is equal to 1, I have, that is equivalence ratio of 1 is equal to 0.46 meters per second. If I go to butane air, C4H10 mixed with air in stoichiometric proportion, the value is 0.4 meters per second. Therefore, we find for these alkanes the speed is around 0.5 meters per second. Mind you, it is quite slow. Maybe if I have a fire which is coming forward, the inference is I can run much faster, and therefore, I can save my skin from the fire which propagates out from an ignition source. Well, let us put down 1 or 2 more. Let me put down the value for acetylene. See, acetylene we said is higher energetics, and therefore, it has a value of 1.6 meters per second. And if I take the last one, maybe hydrogen air system, the speed is around 2.9 meters per second. Hydrogen is a very light gas. If it is a very light gas, the value of rho u, that is in the denominator we have rho u is small and the speed is higher. Well, these are about the speeds, and therefore, we have done something now. See, we are now able to find out if I have a gas mixture and if I sort of ignite it, and if by chance I have a combustion wave which I am able to create, I am able to find out the speed at which this combustion front propagates out. When I say combustion front propagates out, if we go back and look at the textbooks on explosions or even on combustion, you will find people talk in terms of flame velocity. Is flame velocity same as the combustion front which moves, or we say the value of SU, which we said is the velocity with which the unburned gases are moving towards the front, is it same as the flame velocity? Let us go back and look at a particular experiment. Let us say I have a tube in which gases are there, and then I ignite the gases and form a flame, and this flame moves out at a given velocity. Now, when the observer is standing over here outside, a stationary observer, he watches the flame go by and he defines this as the flame velocity. Now, what did we tell ourselves? When I talk in terms of that the speed SU, what did I presume? I said I am standing on the combustion front and I am looking at the speed with which SU is coming towards me. Therefore, SU is equal to flame velocity only when the gas ahead of the flame is stationary, but if this is also moving at some velocity, what is perceived as flame velocity is a much higher velocity, because it is with reference. See, I do not take care of this, I presume here that it is stationary, and therefore, I calculate this. Therefore, flame velocity is going to be the unburned gas velocity or the unburned speed plus the velocity of the particular medium in the direction at which the flame propagates. Therefore, we will do some problems involving flame velocity and get this concept to be further clarified as we go along. Therefore, now we say, well, I know the speed with which a flame or a combustion wave propagates, and which I call as the unburned gas velocity. Now, if I say unburned gas velocity, we also find it was proportional to under root k, that means the thermal conductivity. Whenever something is moving, see, I can not only have the transfer of heat by conduction, it could also happen by convection, and especially if something is very turbulent, what could happen? Well, I could have an equivalent conductivity which is very much higher. Therefore, I can also say, well, the SU which I have learned so far, or which I have been able to develop so far based on this mind model, is only good for a laminar case, in which the transport of heat is by molecular conductivity k over here. If it is going to be turbulent, well, I can use similar expressions, but I must also take care of ADs which increase the value of the thermal conductivity, and therefore, I can also say, well, the flame can move at turbulent speeds, which I call as ST as compared to SU over here, and the turbulent flame speeds are generally around 10 to 100 times faster, because the transport of heat from the ignition source or into the succeeding layers is very much higher. The transport by diffusion of the concentrations is very much higher, with the result that the turbulent flame speeds or turbulent burning velocities are very much higher. In fact, maybe towards the end of the course we will see, or maybe towards another 5 or 6 classes, maybe we will see that we can have turbulent velocities which can reach something like the sonic velocities, which we will sometimes refer to as choked burning, choked combustion, because sonic corresponds to choking. Anyway, we have to do all this, but let us now come back. We say, well, it is possible to have turbulent propagation, and when you have turbulent propagation of the burning gases, I say, well, I have turbulent speeds at which it goes. With this background on speed of propagation, can I go back and say what is the thickness of my flame? See, we also said, yes, I am interested, let's again not lose track of the problem. I have a particular volume, I want to find out what is the critical ignition kernel such that a flame propagates out. We are now able to find out the value of SU, or we say, well, ST will be much larger than SU. Can I also find out what is the thickness of the flame which propagates out, because that will help me to do this problem. Therefore, I am interested in the thickness of the flame. Let us again put the diagram of the flame as we looked at it earlier. Well, I say rho u into SU comes here, it increases in temperature from Tu to an initial value Ti to the burn gas value Tb over here. Therefore, what is happening? This is the zone length L in which chemical reactions are occurring. This is the zone in which preheat is taking place, and you have, if I plot the temperature, what is the temperature distribution? Something like this. This is the inflection point over here, Ti, the inflection point over here. Well, what is it? This is the scale is for the temperature. The temperature is Tb here. I have Tu over here. This is the type of progression what do you find. Now, if I were to get the thickness of the flame, well, I am looking at the thickness of the flame to be over here, thickness of the combustion front Tf over here. I want to get an expression for it. Therefore, in a similar way, I just put down the values. Well, I tell myself, well, the heat transferred, let's put it down here. I have rho u into Su is the mass flux which is coming, and what happens? I'm interested in the total. Therefore, I have Cp into I get the value of Tb minus Tu, which is the total. And what is it? You know, this is the total heat which is being generated in this, and this heat is what is available here, and therefore, the total heat is going to be equal to the heat which is generated, which is equal to Tf into omega into Q. But the heat which is generated is also the heat which is conducted away. I can write it as equal to K into, if I assume the gradient to be Tb minus Tu, and the thickness of the flame front as Tf, this is equal to Tf, and therefore, what is it I get? I get now the value of rho u into Su into Cp into Tb minus Tu as equal to, well, this is common to this, I get the thermal conductivity into Tb minus Tu into Tf, and therefore, on the left hand side I have Tb minus Tu, on right hand side I have Tb minus Tu. I can knock it off over here, and what is it I get? I get the value, this mind you is equal to the thickness of the flame small Tf, therefore, I get Tf is equal to, I bring it on this side, I take the rho u Su Cp on this side, I get rho u into Su and Cp over here, and therefore, I get the expression for the thickness of the flame to be K divided by rho u Su into Cp. Now, well, this is the thickness of the flame, but we must be able to get a idea of the thickness. Is it 0.1 mm, is it 1 meter, is it 1 centimeter? And therefore, let us take a look at this particular expression. When I say K over rho Cp, when I say the expression of K over rho Cp, we call it as thermal diffusivity alpha. And what does thermal diffusivity actually represent? It says how much heat is there in a given substance, and out of this heat content of the substance, how much gets diffused out by conduction. That is what? That is the rate at which heat leaves the inertia of a system, and therefore, compared to the heat which moves out, how much heat is contained within the system. That means, how much heat gets diffused out of the system, we call it as alpha, and K by rho Cp as alpha. And if you look at unit of thermal diffusivity, we have unit of thermal conductivity, and what is conductivity? Watts per meter Kelvin, that is joules per second by meter Kelvin, divided by rho, that is Kelvin over here. You have rho is kilogram, rho is equal to kilogram per meter cube density, specific heat again joules per kilogram Kelvin, and therefore, kilogram gets cancelled, joule gets cancelled, meter cube, meter square comes in the numerator. I am left with a second. The unit of thermal diffusivity is meter per second. Therefore, you find I can also write the value of the flame thickness. Let us put it down. I can write the value of the flame thickness Tf small t with suffix f as Tf is equal to thermal diffusivity divided by the flame speed, and we also already saw Su is typically around 0.5 meters per second for hydrocarbon air mixtures. If you look at the thermal diffusivity of most of the gases at atmospheric pressures, it is typically around 0.5 into 10 to the power of minus 4 is what we are talking of, is of the order of so much meters per second, unit being this. The value of Su is, we said, is equal to 0.5 into so much we are talking of meters per second. Therefore, the thickness of the flame is so much meters, well the unit is all right, and therefore, we say that the thickness of the flame is typically around 10 to the power minus 4 meters, or which is around 0.1 meter. Well, the thickness of this combustion thickness, or the thickness of this combustion, which consists of the preheat and the zone of chemical reactions, is only of the order of 0.1 millimeter, because it is 10 to the power minus 4 meter of the order of 0.1 millimeter, and therefore, we can also say it is as good as a wave. You know, the flame is so thin that it progresses as a wave. Therefore, we have two expressions now. We derived an expression for the flame speed SU. We also derived an expression for the flame thickness TF. I would like to use these two to be able to find out how much energy, if I do not use the lumped mass system, but if I am interested in having a kernel of a given size, I would like to know how much energy is required to ignite it. But before I do that, one last derivation as regards the combustion wave. What is the pressure generated? What is the pressure behind a combustion front is what I would like to do. And if this is clear, well, I can go back and justify some of the things I have been doing today, and also have an idea of how to go ahead and model my ignition required, my size of my kernel what I require, and therefore, proceed further with my combustion waves. Therefore, I tell myself, well, I am looking at this. I now know I have a flame which is of thickness TF. I have something which is moving here with a speed SU towards my front, and what is moving is rho u, SU, and at a temperature TU. And what is here on the right hand side is what I have the burn gases, and into the burn gases the combustion front moves with, or the gases are moving towards the combustion front, which is stationary, because we considered SU with reference to the observer sitting on the wave, that is with respect to the combustion front itself. Therefore, gases are moving at S, gases are moving a wave over here, the density is rho b, the speed is SB, the temperature is TU, the pressure is, let us say, PB, TB over here. If I write the momentum equation, what is it I get? Well, I have pressure upstream, which is equal to Pu, plus I also have the momentum. I am considering unit area. Therefore, I say, or the flux movement, either the flux or I have area, that means area into pressure is the force, and I now write the total mass, which is equal to rho u into SU into per unit area. I have this into the SU square. This is the result of the pressure and the momentum on this side, which is equal to the value of Ps plus rho s into, I have rho b, here it is Pb over here, Pb plus rho b into Sb square over here. Therefore, I get the value of Pu minus Pb, that is the change in pressure from here to the burnt gases over here, is equal to, I get rho b into Sb square minus rho u into Su square. But from continuity, I also know that the mass flux coming here is equal to mass flux leaving here, or for per unit area, I can write as rho u into Su is equal to rho b into Sb, and this being equal, I can write it as equal to rho u into Su into, I get Sb by Sb minus Su. I take this is equal to this, without this over here I am left with Sb minus Su, and now I take Su outside, get rho u into Su square into Sb by Su minus 1, but Sb by Su is equal to rho u by rho b, and therefore, I write the pressure difference. Let's write that out. I get the value of Pu minus Pb is equal to rho u into Su square into, I get Sb by Su from the continuity equation is equal to rho u by rho b minus 1. You know, the burned gases are at a higher temperature than the unburned gases, therefore, this is greater than 1. Well, I have the, therefore, what is going to happen? Therefore, I say, well, Pu is going to be greater than Pb. That means there is a drop in pressure across the combustion front or the combustion wave. And what is the magnitude? Let us just put down the magnitude for one specific case. Well, the ambient pressure is something like 1 atmosphere 300 Kelvin, therefore, the density rho u is typically around 1.2 kilogram per meter cube. We said, well, SU for most of the cases is around 0.5 meters per second for hydrocarbon gas mixtures. The value of rho u by rho b, if I say that the temperature increase is threefold from 300 to 900 or 1000 Kelvin, rho u rho b is equal to something like 4, let us say 4 times the increase in temperature, that is the burnt gas temperature is something like 1200 Kelvin as compared to the initial temperature of something like 300 Kelvin. Therefore, if I substitute these values here 1.2 into 0.5 squared into 4 minus 1, I get the typical value here. If I substitute these values, I get the value of Pu minus Pb is something like 0.9 Newton per meter square or something like around 1 Pascal. Hey, 1 Pascal is a very small number. Atmospheric pressure is something like 10 to the power 5 Pascal, and therefore, even though there is a fall in pressure, the fall in pressure is very small, and therefore, whenever we talk in terms of a combustion front, we talk in terms of a constant pressure process, and that is why we are justified in using the value of Cp while determining the flow properties over here. That means, across a combustion front there is hardly any change in pressure, but mind you, let us keep this clear, there is a drop in pressure and this drop in pressure is somewhat small. Therefore, so far what is it we did? We have learned the following. We learned how to determine the value of the flame speed SU, which is the unburned gas, that is the velocity with which the combustion front is moving into the unburned gas medium, which we said for a stationary medium is same as the flame speed. We also talked in terms of the thickness of the flame, which we said is equal to thermal diffusivity divided by the speed of the combustion front, and also we talked in terms of the pressure drop across a flame, which we said is extremely small, but there is a small drop in pressure across the front. Now, we want to put these things together to be able to relate how much energy is released in a in the zone. We want to estimate the size of the ignition kernel, and to be able to do that, I want to define one last thing, namely, is there something like a length scale which can say, which will not allow, let us say, a flame to propagate. Rather, let me formulate this. Let me say, supposing I have a pipe like this. Well, we know now, yes, I have a combustion front, into which I have, this is stationary, I have rho u, SU moving towards it, I have rho b moving at a speed SB behind it. Is there a specific dimension d beyond which I cannot allow my flame to propagate? That means, I want to look at, maybe if I have the flame structure over here, I have the flame over here, you know what is going to happen? I have the walls of the pipe over here into which maybe gases are moving towards the flame, maybe the flame we are telling is stationary, we are looking at the problem in the frame of reference of the flame. And what I want to do is, I want to see what is the heat which is getting transferred from the flame to the wall. I want to take a look at what is getting generated over here. Therefore, I want to find out the diameter for which a flame is just able to propagate in this. Is there something like a diameter below which the flame cannot propagate, or rather a diameter by which the flame will get quenched, and therefore, what I will do is, maybe I will take a look at the quenching distance or a quenching diameter, and based on this quenching diameter, I will put the quenching diameter along with flame speeds to be able to define something like the critical size of the ignition kernel. I will follow this up in the next class, and therefore, to just review what we have done today, we find that we have relaxed the assumption of, let us say, a lumped mass system. We looked at the ignition of a gas at a particular point, and therefore, from this point the flame or the combustion wave propagates ahead. We said, yes, I now know how to estimate the speed at which the combustion wave propagates. I know the thickness of the flame, I know that the pressure drop across the flame is extremely small, even though there is a drop across the flame from the unburned towards the burnt side, there is a drop. And now, we will do in the next class the quenching thickness, that is a quenching distance, and thereafter model the ignition. Well, thank you.